back now, and I wanted to continue the topic of how many hours of sunlight should any place on Earth expect. And we had done a video for the length of the day for a circular Earth, if we model the Earth as a circle. Now I want to generalize that and include the fact that the Earth is a sphere. So what we had done in that video is we had taken the ratio of this length, the length from any point depending on your latitude, the length from here to here, to the ratio of the total length, and we had come up with some equation. But we find that when you do that, the number of hours of sunlight that you anticipate for a certain latitude ends up being more than actual, because you're modeling it as a circular Earth. So now let's do the model as a spherical Earth. This line actually forms a sphere like this, a circle like this, right? Because it goes around and it comes back to the other side. And so it goes like this, and then it goes like this, like this. And so what we want to calculate is what part of the day are you inside of the light. So depending on your latitude, you're going to be here, you're going to be sunlight, and over here, and then this part you're going to be in darkness. Okay? This portion of the day you're going to be in darkness. So what we need to do is come up with a way of calculating what this length is that you're in sunlight, and divide it by the total length, the total radius of that circle. So let's do it this way. The radius of this circle is going to be r cosine theta. R cosine theta. Now, how do we know that? Well, because from that video, we had calculated that if this is the radius of the Earth, and this is theta, then r cosine theta would be this thing. So it would give you the radius of this circle. Okay? So we had already done that. And we had gotten r cosine theta was the radius of that circle. Then we had added that to that little distance here. Okay? So this is the radius of that. Now what we need to do is to draw like this, and to focus in, to break this into a straight line here. And I want to know what is this distance here, from here to here. And because eventually what I want to be able to come up with is an equation that represents what this angle is and what this side of the circle is. So the time we had calculated that this distance d, which is this distance, okay, that distance d had been r sine of theta times tangent 23. R tangent 23 and a half sine of theta. So because it was the radius of the Earth, r, times sine theta, which one was this portion, this is r sine theta, and then times tangent 23 would give you this distance here. Okay, this little distance, that's that distance. Okay, so now if I call this piece here alpha, okay, so let's draw this a little bigger. If I call this piece alpha, and then I have a straight line here, alpha, and then this is d. This distance from here to here is d, and this is alpha, and this is my radius r cosine theta. So I'm going to say cosine of alpha is equal to d divided by r cosine theta. And then my d is going to be this equation. So you're going to have r tangent 23 and a half sine theta divided by r cosine theta. R and r are going to cancel. Cosine of alpha is going to be tangent 23 and a half times tangent theta. So that's going to be that angle. And then therefore, alpha is going to equal cosine inverse of that. Okay? It's going to give you, depending on if you do this in degree mode, it's going to give you an angle in degrees. If you do it in radian mode, you're going to get an angle in radians. So now what we're going to argue is here, along the arc length, call that S. S is equal to the radius of the circle, r cosine theta, times twice the angle. Right? Where do we get that? Well, from geometry. Any arc length of a circle is equal to its radius times the angle, the subtended angle, but you have to measure that in radians. Measured in radians. Okay? Let's say we don't want to measure in radians. Let's say we want to be able to do this because you see this 23.5 degrees is in degree mode. And so we don't want to keep changing from degrees to radians. So since this is degrees, let's keep this in degrees. We're going to get an answer in degrees. So if we get an answer in degrees, how can we change that to radians? Then you can convert. So what we can do is we can say the S is equal to r cosine theta times, and then this 2 we can just bring here, 2r cosine theta, and then alpha is going to be cosine inverse of tangent 23.5 tangent theta times, now this is, if we want, this is going to give it to us in degrees, and then we can say 180 degrees is pi radians. That means I can keep this in degrees, keep this in degrees. This whole thing will give me degrees. This one will convert it to radians. The 2 will come from the 2, and then the r cosine theta. That's going to give me this arc length. Okay? So now, how much of the day are you in sunlight? This whole is sunlight, right? From the whole circumference, right? The circumference of the circle is 2 pi times the radius, but the radius is r cosine theta, right? 2 pi r cosine theta. So if I subtract the S from 2 pi r cos theta, I'm going to have minus S. So now here's what I'm going to do. Circumference minus S divided by the circumference. That's the ratio of how much a person is in the sunlight divided by the dark portion. Okay? Sunlight divided by dark. So C minus S over C, 2 pi r cos theta minus S over C. Okay? So what do we get by that? And then we're going to get 2 pi r cos theta minus this whole thing. Okay, so when we divide them, what do we get? Well, this whole thing cancels with this whole thing. The 2 cancels the 2. The r cancels the r. The cosine theta cancels the cosine theta. Pi cancels the pi. Most everything cancels. So you have is equal to 1 minus, and you end up getting just cosine inverse of tangent 23.5 tangent theta divided by 180. Okay? So the number of hours of sunlight for any latitude will be equal to this ratio times 24 hours. So it's a very different looking equation than the one that we ended up with when we modeled the Earth as a circular object. This angle, however, the 23.5, is only true, remember, on June 21st. On any other day, we're going to have to first find what the deck angle of the sun is, and then use that angle over here to calculate what the number of hours of sunlight is. So that, that equation is equal to the deck angle of the sun is equal to 23.5 sine 360 t minus 80 divided by 365.25. So if you're given a certain day, you put that time there, you figure out what the deck angle of the sun is, then you put it into here, then you do your calculations for the number of hours